Alright, this lesson is for Unit 9, our first lesson on circles and tangent lines. If you were absent, hopefully this will at least get you caught up to where we're at. Unit 9, we're just starting, so we've got 6 lessons, and today just focusing on tangent lines in circles. We're going to have a bit of vocabulary words today. You should be familiar with what a circle is. It's a set of all points on a plane that are equidistant from a given point called the center of the circle. We often name circles after their centers. So if the center is point P, we would call this circle P. And you'll see the notation written like circle P. A radius is any segment in the circle that connects the center with one of the points on the edge of the circle. You should, I think, be familiar with radius. Chord is probably a new word to you. Chord is a segment that connects any 2 points on the edge of the circle. So it's the endpoints of the chord are on the circle. A diameter is a special chord. It's a chord that includes or contains the center of the circle. So a diameter is a type of chord. The other 2 vocabulary words are lines. If we're looking at this other diagram here, a secant is a line that intersects the circle at exactly 2 points. And then we have a tangent line here at the bottom. A tangent line intersects a circle at exactly 1 point, and we call that point the point of tangency. Sometimes people confuse secant and chord. A chord is sort of a portion of a secant. The secant is the entire line, and the chord is just the portion of the line that is on the inside of the circle. So looking at this diagram, we can classify each of these parts of the diagram as either a chord, a radius, a diameter, a secant, or a tangent for circle B. So B is the center of that circle. So the first one asks us what AC is. AC is here. It's a chord inside the circle, and it contains the center, so we call that a diameter. The next one, from A to B, that would be from the center to the edge of the circle, so we would classify that as a radius. Next, we have line AG. So we want to classify this line. Well, line AG intersects the circle at 2 points, so we would classify that as a secant line. The next one is DE. On our diagram, DE is this line here. It intersects our circle at exactly 1 point, point C. So we would call line DE a tangent line. Segment HI. Segment HI is here, and we call that a chord. The last one is CE. Now, on the notation there, you might notice that it just has a 1 arrow. So this is technically a ray, not a line. We would still classify it as a tangent. It does only intersect that circle at 1 point, and if we extended it, it wouldn't intersect at another point. So that ray does count as a tangent. We will, as we work in this section on tangents, we will oftentimes just have tangent segments, like just parts of the tangent line, and that's fine. There's no problem with that. They still count as tangents. As long as if you extended them, they would only intersect the circle at that 1 point of tangency. Okay, a couple more ideas. If you have 2 circles on a plane, there's a few possibilities for how those circles might compare to each other. If they are overlapping at all, they're going to have 2 intersection points. And they won't have any more than that. They'll just have 2. There's not a way to get exactly 3 intersection points, just 2. So we have the possibility that the circles might overlap and have 2 intersection points. If the circles have exactly 1 intersection point, it's either the case that they're side by side and they share that common point, or it could be that one circle is inside the other and they share that point. These are called tangent circles when they just have that 1 point in common. And I think you'll see some tangent circles come up on your assignment. The other possibility is that they might not intersect at all. The 2 circles might be sort of just hanging out nearby each other. It could be that they are concentric circles. That means that they share the same center point. They just have different radius. It could also be that they're inside one another but not concentric. We are going to be looking at for a second this situation where the 2 circles are just sort of sitting near each other but not having any intersection points. If that's the case, if you just have 2 circles near each other, they will have some common tangents. If the 2 circles are on the same side of the tangent line, that tangent line is called an external common tangent. It's common to both, and it's to one side, so external. If that tangent that they share is between the 2 circles, we call it an internal common tangent. For any 2 circles, they share several common tangents. Let me show you. So if I have any 2 circles, I can draw several common tangents for those 2 circles. Let me get some. Okay, so they're going to have an external tangent on one side. Let me line that up a little better. And then they'll have another external tangent on the other side, if I can line it up right. Oh, that one does not want to line up. So they have 2 external common tangents. And then you can also find some common internal tangents. Let's get a different line color for the internal ones. Oh, that's funny. Sorry. Okay, new line. We're going to make these ones red. The internal tangents go between the 2 circles. So it will have 1 that goes between the 2 circles in this direction, and then it will have another one in the other direction. So for any 2 circles, you're going to be able to draw, or you would be able to find 4 common tangents, 2 common internal tangents and 2 common external tangents. Okay, so we have 2 theorems about tangent lines and circles. Here's our first theorem. If you have line M tangent to circle Q, then we know that line M is perpendicular to the radius of the circle at the point of tangency. So if we know P is the point of tangency and we create this radius right here, that's going to be a 90-degree angle to line M. And it works both ways. If you know 90 degrees, then you know it's tangent. If you know it's a tangent, then you know it's 90 degrees. So because these tangent lines are creating 90-degree angles, we often use trigonometry and triangles to help us solve problems. So these first 2 examples, we're going to use Pythagorean theorem to help us. So our information that we know is that AC is tangent to circle B. Well, C is the point of tangency, so we know that this is a right angle. Our goal is to calculate the length of AB. So we want to know the distance between A and the center of the circle. Well, that right angle right there is creating, or showing us a right triangle, and we can use the Pythagorean theorem to help us. Leg squared plus the other leg squared is equal to the hypotenuse squared. I'm just going to call it AB. So we've worked with the Pythagorean theorem quite a bit lately, so you should hopefully be familiar with it. You can use your calculator to add those two squares together, and we end up getting 625 is equal to AB squared. And then we can take the square root of both sides of our equation, and we find that 25 is equal to AB. Okay, so this next one is similar, but a little bit different. In this diagram, we have ST tangent to circle R. So we know we have a 90-degree angle right here, creating that right triangle. And our goal is to figure out the value of x. Well, x is not from R to T. It is not that entire hypotenuse. X is just this portion. So in order to find the length of x, we are going to calculate the hypotenuse length. But then we have to use a little bit of logic to help us finish the problem. If you look at the diagram, you can see that the radius of the circle is 5. But right here, this portion of the hypotenuse is also a radius of the circle. So it also has a length of 5. So once we know the entire length of the hypotenuse of that triangle, we can just subtract 5 in order to find the length of x. So for the Pythagorean theorem, leg squared plus other leg squared is equal to hypotenuse squared. I'm going to call it C for now. So if we solve that for C, we add the 5 squared and the 12 squared together in our calculator, and then we take the square root of both sides. We find out that the hypotenuse is 13. So we know this entire length is 13. Well, 13 has to be 5 plus x, because we add those two parts of the hypotenuse together to get the total 13. So that means our segment length, the length of x, must be 8, because 8 plus 5 is 13. Okay, we're going to get into a little bit trickier application problem here. We, this time, want to calculate the radius of the circle. So in both of our last two examples, we knew what the radius was. So in this example, we are trying to figure out the radius of the circle, which I'm going to write R for radius. We have two radii shown. We have the one from C to B, and then we have the one that's going in the direction of point A. Well, we can still use the Pythagorean theorem to help us solve this, but this length right here in our diagram is broken up into two pieces. We have this part of it that has our length, the part that's inside the circle, and then we have this part outside of the circle that has a length of 9. Well, if you have two parts of a segment and you want to know how long it is, you add them together. Like if I have a section that's 2 and a section that's 4, the total is 6. So if I have a part of the hypotenuse that's R and a part of the hypotenuse that's 9, the hypotenuse is R plus 9. So when we do the Pythagorean theorem, we want to put the leg squared plus the other leg squared And that needs to be equal to the hypotenuse squared. Hypotenuse is r plus 9. To show squaring that, we need to put it in parentheses. So this problem is quite a bit more tricky than the last one we worked on. So remember the squaring something. If I have a second power, that just means times that thing by itself. So our problem is that we need to multiply the r plus 9 by r plus 9 times it by itself. Well, this is a binomial multiplied by another binomial. Remember, we have to do a lot of distributing to times these two together. So we first multiply the r by both r and by the 9. That's r squared plus 9r. And then we have to multiply both of them by 9. 9 times r is 9r, and 9 times 9 is 81. Remember, when we're multiplying binomials, we often have two terms that can be added together. Not every time. We're not guaranteed to have two terms that can combine, but most often we do. So this is r squared plus 18r plus 81. Now, on the other side of the equation, if I evaluate that 15 squared, I have r squared plus 225. Okay, so we need to solve this for r. Well, let's see if we can get these r squareds together. I'm going to subtract it. And I have to subtract from both sides, and oh, look what happens. The r squareds actually cancel out. So let's see. We're still working on trying to get r by itself. So I have 225 equals 18r plus 81. I'm going to go ahead and subtract the 81 to get those constants combined. So I now have 144 is equal to 18r. And our last step would be to divide by 18. And then we'll know the length of the radius. So our solution is that the radius must be length 8. So definitely that's a challenging problem. It has a lot of steps to it to calculate the radius. There's 3 on your homework that are like that. So if you're having problems with those, let me know and I can help you get the hang of them. Okay, for purposes of the video, I'm skipping this. We're going to go to our second theorem. So the second theorem has to do if you have two tangents coming from an external point on the circle. So, for any point outside of a circle is possible. So if I just draw a random circle and pick a random point, it's always possible to draw two tangent lines to the circle from that point, one on each side. Those aren't perfectly straight, but hopefully you get the idea. Our theorem says that if you draw those two tangents, then the length of those two segments connecting the point to the tangent point on the circle, those are going to be equal to each other every time. They will have the same length. So we can use this to solve some problems. So for this diagram, first diagram, we have ML and NL, both tangent to circle P. Well, because they're both tangents to circle P, we know that they are equal to each other in length. So 15 minus x is equal to x plus 4. And we can solve for x fairly simply by bringing our x terms together and bringing our constants together. So if we do that, we end up with 11 is equal to 2x. Remember, sometimes coefficients of 1 give people troubles. That's just a 1x plus another 1x to equal a total of 2x. And then we'll divide by 2 to get 5.5 as our solution for x. Okay, on this next diagram, it shows us that those are right angles, which means that we have some tangents here. AB is tangent to the circle and AC is tangent to the circle. So if we would like to solve for x, we know that those two tangent segments must be equal to each other. X squared plus 6x, whoops, I'm sorry. We set them equal to each other. X squared equals 6x plus 16. Now, we haven't dealt with equations like this for a little while. It was before Christmas that we worked with these. The power of 2 on that x term, x squared, that tells us we're going to have two solutions to our problem. We want to find these solutions by factoring. So I'm going to go ahead and subtract all of the terms over to one side of the equation. So I get x squared minus 6x minus 16 is equal to 0. And then we can factor it. So we first focus on our leading term, x squared. That tells us that our factors are going to lead with x's. Together they multiply to give us the x squared. Over on the other end we have a 16. So it could be 1 and 16, it could be 2 times 8, it could be 4 times 4. Those are all the possibilities for the number 16. We have to consider our middle term of negative 6x. So I'm going to choose this combo. To get a negative 6, I need the 8 to be negative and the 2 to be positive. So there are two factors, x minus 8 and x plus 2. And remember, to get the solutions, we set each of those factors equal to 0. So our solutions are 8 and negative 2. Now, you won't have to factor a lot this unit. Occasionally they come up, and we'll try to be practicing and remembering how to do that more and more as we approach the end of the school year. Okay, last one. These are pretty fun, I think. So we've got a circle that's inscribed in a quadrilateral. Now, not every quadrilateral can have a perfectly inscribed circle like this, but this one can. So we've got tangents on all four edges of that quadrilateral. All of these points are points of tangency. Our goal is to find the perimeter of this quadrilateral, and we'll use the tangents to help us. So I'm going to start with point B at the top. If this length of this tangent segment is 10, then that means this one to the other tangent point must also be 10. And changing over to point C over here, if this portion or this tangent segment right here is 5, then that means this one is also 5. Over here at point A, we know the length is 3 on this point on this tangent segment, which means this segment also connecting point A to the circle at a point of tangency, that must also be 3. And we're really close to finding all the lengths. We just have this length down here from D to the circle to figure out. Well, we know the whole length is 12, and we know this portion is 5, so this part must be length 7, which means this one is 7. So to find the perimeter of the quadrilateral, we just need to add up all of those sides. So we've got one side that's 13, we have one side that's 15, we have this side that it gave us that was 12, and we have one more side that's 10. So the perimeter is 13 plus 15 plus 10 plus 12, and if we add that up, we get that the perimeter is 50. Okay, so hopefully if you were absent, that will get you caught up with what you missed. And that was lesson 1. The homework assignment in your packet that goes with this lesson is pink. Let me know what questions you have. Thank you.